Good. All right, we're going to get started with the lecture today. So you guys are section one. And all right, so this is the last lecture. Okay, so we are finishing up um, the semester. Next week is what? Term project presentations, right? So that's your only chance to present. We have plenty of time for everyone to present, but that's it. Okay. So don't forget, term project presentations are a week from today, and then 2 weeks from today is the final exam. Okay. All right. So today is essentially the last day of lectures. Um, Before I get started, are there any questions? No? All right. Good. Everyone needs to present. It's just remind you, the term project is 20% of your grade, so pretty significant. All right. Yeah, and then you have one last homework assignment, right? Related to image processing, images. It's very simple. So you have, I think, until the last day of class, so about 2 weeks to finish that up. There won't be any homework associated with this topic. This is one of the more advanced algorithms, still in the sphere of images, right? But very interesting things as far as it gets into generative AI and all those ideas, right? And so that's essentially. All right, so we're gonna get started. So you guys, we had class last week, right, on Monday. So we covered, we finished up, we've covered CNNs for sure, and then we've done losses, batch normalization, loss functions. And so today, as time permits, I will go over just the last few topics. Um, and I'm going to create the folder here for this one. So one of the first algorithms related to images and generative machine learning would be something called GANs. So generative adversarial network. So that's something that you should be able to understand because it actually builds off of what we did when we looked at CNNs, right? So it builds off of that. Very interesting idea. So I'm gonna add this. I'm gonna call it GANs. And essentially, I just have a few links, similar to everything we've done before, a link for reading material, and then, like a blog post type, and then the code. Okay? So we'll go over the code today. And then on supervised learning, as time permits, will be also covered very interesting ideas there. Okay, so here is GANs. So I'm going to move this right there. Okay. And I'm going to provide, I'm going to create a link for the notes. And this is going to be the notes. And so it's just going to be here. So it should be here. And it's generative adversarial networks for GANs. So I'll provide this link. Whoops. There. All right, so that link has been added. Contents. And then I will also provide the code for this. This is the example that we're going to go through today. But as you might imagine, a lot of it, 70% of it, you already understand. It's similar to you. But this now starts to get into some interesting new ideas, right? So this will have an idea that maybe you've never thought about. And if you remember, when I was talking about NIO, right, I kept saying there's something that has this strange feeling also, like NIO, which is called GANs. It's just an expansion of an idea. So let's go to GitHub. So it's going to be on the GitHub. This is, where is it? Here it is, GANs. You can click on that. There's going to be lots of things going on here. So there's actually something called just plain vanilla GANs, and then there's CGANs. And CGANs stand for conditional GANs. So they get into the first, you know how you guys use Sora or you use Stable Diffusion and you type some text, right? And then you get an image, right? I'm sure all of you have tried this. Even ChatGPT will do that. Well, CGAN is like the, the precursor to that, right? So the ancestor. And in CGANs, what you can do is at least you can give it like one vector, a little vector, and that vector is input so that the image that you generate is now within that context. So I think, we've talked about LLMs and everything like that, so you should be able to see how this could be expanded further. But that's kind of what I'm going to do today. So we're going to cover GANs and then extend that to CGANs and just show you. And you'll see it's, just like an additional part that you're adding there. But I'll provide this link for the code. So I'm going to go here back to table of contents. And under GANs, I'm going to create a link. And this is just going to be the code for both Jupyter notebooks, okay, of GANs. So we're going to, all right, and that's done. Okay, so I'm going to stay within the context of MNIST. We've seen, how to use the MNIST data set for classification, and now I'm going to use that same data set for generative, and then I'm going to use it for conditional generative approaches, okay? And we're going to train it from scratch. That's like the amazing thing, right? Totally no transfer learning, none of that. No magic model that already does it. You're literally building it from scratch, okay? So very powerful. So we have both here. So let's go ahead and I'm going to close this here. So now let's click on just notes to kind of illustrate. So remember, for the exam, this is, the material that you should be reading through. All right. I'll talk about this a little bit, but this is, read through this. And then, of course, I get into explaining the code and all of that. And this is what we'll be doing. So as you can see, that is what? A 0, right? So we're training a model so that it can generate the digits, the handwritten digits. Okay. And that some kind of a 5 or a 3 or something, and then we have the conditional GAN. So let's get into it. Just a little bit of the introduction. I'll let you guys figure out, read the rest. But I'll just jump at the code in a second. This is the graph of a generative adversarial network. All right. This was invented by Ian Goodfellow in around 2014. So you can see how really quickly this algorithm was invented before the transformer. Between 2014 and 2017, it was the most amazing thing that existed. And everyone was dazzled by it, and then transformers came and everyone like, wow, right? So that's kind of the idea. And then you can see the context since 2017. Been 8 years. There hasn't been anything. There's been a few things. Stable diffusion, I would argue, is another one that's pretty nice, but really not that many other algorithms. All right, so how does a GAN work, right? So a GAN works, you have 2 models, okay? So everything we've done this semester has been one model. We would, use one model or another model, but always independently, right? So they were both, we were just trying to add more architecture, and so we were always replacing them. But this type of model has, or this type of algorithm, I should say, uses 2 models at the same time. All right, that's why it's called a generative adversarial networks, or GANs. So one model is the generator and the other one is the adversary, which is nothing more than a classifier. So it's exactly the same classifiers we've seen all semester. The generator is a little bit different. It's something new that we haven't really seen If you remember with neural input optimization, we're optimizing that input, right? We meet some constraints that we have to define in the loss function. But in GANs, you can imagine it's a similar idea, but instead of us defining the constraints in the loss function, we train another model with data to make that decision and provide that feedback. Okay, so that's the idea. So we have two models. It would be these two square boxes. One is a neural network called a generator. The generator generates something. In this case, because we're going to talk about in the context of images, okay? I'm just going to say images, but you can imagine it's just any embedding or a vector or something like that. Now notice that just like in NIO, we start with some kind of random input because neural networks need an input, right? But in NIO, we were trying to optimize the input. Here, we're not optimizing the input because what we're training is actually the weights of the model, right? In NIO, we freeze the weights of the model, correct? Here, we train the weights of the model. So in that sense, it's a traditional neural net, right? So we're training, but we're actually training together the weights of both models. Think about that. So GANs are very elegant, but also have a problem that sometimes it is, if you were thinking that training one model was difficult, imagine now two models, right? Which are technically like fighting against each other. Like one is trying to be better than the other. And what you want is you want a balance between both models. Do you guys see that? So that's essentially what a GAN is doing. So random data goes into the generator, and the generator in this context generates an embedding, a vector, which will be, in this case, an image. Okay, so this is an image. And so the image then goes into, that's done, right? The generative part is done. We have an image. Now that image goes into what? Another model, a discriminator, which is like the CNN classifier that we built at the beginning of the semester. All right, so the image goes into the discriminator, and what does the discriminator do? It classifies it as real or fake. All right, so one analogy that a lot of people use is that you have like, let's say a lot of us like art, right? So we like paintings. We've all heard of what Picasso and Da Vinci and stuff like that, right? So, but imagine that there's also forgers, right? So there's a forger that tries to create paintings and wants you to pay millions of dollars for something that's a forgery. Do you guys understand? So that's what's happening here. So the discriminator, this one over here, this neural network, is like a cop, and it needs to learn to differentiate between forgeries and real paintings or real images. So real paintings are just data. We have examples of what a real painting looks like. So whenever a real painting from the real data goes into the discriminator should say true or real. Do you guys see that? But it also needs to learn that when it gets a painting or an image created by the generator, generated by the generator, then the discriminator should learn that that is false or fake. Do you guys see that? So essentially the training process is going to work like this. We're going to have real images. Whenever we train the discriminator that whenever there's a real image, it should say it's real. And whenever we get an image from over here, it's a fake. But also there's a third objective, and that is that we also want to optimize the weights of the model to fool the discriminator. Do you see that? So the discriminator has like this dual objective, and we update the weights of the discriminator accordingly. But the generator has its own objective, right? So think about it. When a real image comes into the discriminator, it should say real or true. When a fake image comes into the discriminator, it should say fake or false. But when the generator generates an image, it wants to generate an image that when it goes into the discriminator, it actually says true. Do you see that? So this is how we need to train. So there's going to be now two models, and there's going to be like three optimizations. Two optimizations for the discriminator and one optimization for the generator. So the weights of the generator need to get better and better and better, right? So that when an image is, if an image from the generator is sent to the discriminator and the discriminator says it's fake, then the generator has bad weights. What should it do with that feedback when you back propagate? Improve the weight so that the next image that it generates goes into the discriminator and it says fake. Okay, that you failed again. But what do? Via backprop, you send information to the generator to update the weights, and now you've updated the weights over many times, and guess what? Now the generator makes an image that goes into the discriminator, and guess what? The discriminator says is true. And at that point, you have a set of weights that's pretty good for the generator itself. Do you guys see that? Does this idea make sense? This is one of the most elegant ideas of neural networks, actually. Stable diffusion is a nice idea, but I've always liked this idea a little bit better. A lot of models, as for those of you that take ITS 530, you will see with reinforcement learning through human feedbacks, etc. Now you're going to have multiple models helping to train other models. There's going to be essentially this idea. Imagine in LLMs, when you guys were doing your LLM pre-training, it would have been really nice if you could have just like in real time generated, giving it some text, it generates two or three answers, right? And then a human says, well, out of these three, I think this one's the best. And then you use that feedback to update the model, right? So a human can only do about 10, let's say if you're OpenAI, so it can do 100,000 of those, right? Because they can spend a lot of money on people. But then guess what happens? With all that data, you train a model to do the exact same thing. And now the model can look at three sentences and say, because it learned, I think this one is better just by ranking. Do you guys understand this concept? So that you can see how this is something that you do a lot in with advanced AI, right? So it starts to get into this idea of advanced AI just by having two models. And we're going to do all this from scratch, very simple, and it'll work for sure. But these are the ideas, like when you train the actual chat GPT, pre-training, fine-tuning, reinforcement learning through human feedbacks, which can be manual for a little bit and then automated. So for instance, I heard that in finance, you know how they write all these like really big reports about some financial institutions, right? Let's say you're some famous financial institution, Goldman Sachs, something like that. This is a video I was watching of the entry level positions today, right? So what would happen in the past is you would hire a lot of young people from school with entry level position, for entry level positions, and their job was really to go through these reports, right? Put them together. But what OpenAI has done now is they hired like 1,000 experts in writing these reports, and these experts have been training models like these just to provide feedback of the reports that the LLMs are generating. So that in fact, a lot of those entry level positions are being replaced with AI, right? So this is an example of that. So it's pretty important that you understand this concept, right? That this gets at the heart of AI now doing work. Do you guys see that? So before, if I asked you to do this before this example, right, create a good generator, you probably would have gone in and annotated the images manually, right? But here, no human is really needed, right? So because we can cleverly automate everything through two neural networks. For a more advanced task, you just train the model with a little bit of data from humans that can generate at most 100,000 pairs of questions, answers, or this is a good report, this is a bad report. And then from there, you train a model, and that model can, not just annotate 100,000, but unlimited, right? 1 billion, 1 trillion questions and answers, etc. So so this is how you start at getting AI to do jobs. So as I said in this example, this is very, the only data you need is the real data. This generator generates, you give it random data and it generates garbage, literally. Yes, and then the discriminator takes in, but garbage of specific dimensions, right? Because we're using MNIST, the images are 28 by 28, right, for real, and for the fake, they also need to be 28 by 20. Do you guys see that? And so then through clever use, like elegant, use of optimization, as I will show you guys, the discriminator is the one that's doing all the heavy lifting, and it's gonna force the generator to stop producing garbage images and instead to start producing actual images with the goal of fooling the discriminator. Any questions about any of these ideas, guys? All right, so the way that it's gonna work is initially the GAN generates only random images, right? Because it's just a GAN. So it'll just generate, from the MNIST data set, what is it going to learn? Well, garbage would be just noise, right? Noise images, a whole bunch of things. But we know that the data set is ones, twos, threes, it's handwritten digits, it's MNIST. So eventually it will learn, as you can see over here, that it's learning to produce, that's a 0. That was generated by the GAN. This is something you will do today. All right? Any questions about that? All right, so the GAN generates just random things. But what if you wanted to generate a 7 or a 3 or a 5, like specifically, right? That gets a little bit more at like ChatGPT. You give it some text and it gives you an image of a cat on the moon or something like that, right? Which is what you want. So that's more advanced. That's what Stable Diffusion achieves. Today we're not doing that. We're just doing this example of generating numbers, but condition. And this model is called a conditional GAN or a CGAN. So this is a paper by Misra, I believe. I don't know if I added the reference in there, but you can see here is the graphic to explain the idea. And then we're going to jump into the code, and then you guys can start using GANs, etc., and learning this concept. So what's different? Not much, honestly. We still have a discriminator. That's pretty much the same. Its job is to say real or fake, right? It gets a real image, right? Same as before. Or it gets a generated image. And in the case of MNIST, as I said, they're 28 by 28, but we can, to make this even clearer and simpler without any like abstractions or obscurity, we're going to spaghettify them. So they're going to be vectors of 784, right? Pretty easy to comprehend. The generated image goes in. Now the generator is kind of the same. What changes, amazingly, is that instead of just providing the noise vector like we did before, now we provide the noise vector plus a conditional vector. So this can be as simple as how many classes do we have in the MNIST data set? We have 10 classes because they're 10 digits. So then we just create a one-hot encoded vector of those classes. So essentially a vector of 10. And we concatenate that vector to the noise vector so that we get 784 plus 10. But now whenever we are giving the noise, we also provide the condition, such as 3. Right? So now when you want to use this model, you provide the condition. So you say, okay, 7. So the generator will learn to generate 7s, right? If you tell it 3 one-hot encoded, it learns to generate 3s. And then in the classifier, we also have to differentiate that as well. So that's one addition that we will do, but otherwise is very similar to the GAN. All right? Any questions about that? So this is, your first conditional and generative model. Okay? And so, it's black and white and everything grayscale just to keep the dimensions simpler and, keep the simplicity as much as possible. All right? So we're going to do these now. So I've given you the graphs. Make sure you read through all these materials. You can see here nicely that these are the losses, and you can see that there's a balance, right? There's a balance in these losses. You can see kind of like they want to meet in the middle, but so that because you want to train a really good discriminator, but also a really good generator. You see that? You don't want to be, like a great discriminator that can always figure out what a fake image is, because then the generator never achieves its goal, right? So it's kind of like you're looking for this balance, and we'll see this. Make sense? So let's go ahead and get started, okay? We're going to use Colab and our approach. We're going to go through the code, and you guys can build your first GAN, and then we're going to build a CGAN, and, you'll have your first well, not your first generative models, but certainly for image processing from scratch. All right, so I'm going to close this one. I provided, as I said, to go to the table of contents. Right, I provided this module, GANs, so we're going to click on that one. And now we can click on the code that you can use as reference, okay? So we are going to go, so you can see I have both Jupiters here. I have GANs and then CGANs. All right, so I'll start with GANs. All right, and we're going to get started. You can see it's because I'm using MNIST, it's going to be a lot of the things that we already discussed in the CNNs. I'm not even using CNNs necessarily, right? But you can see how if you use CNNs or something else, it's going to be, could be better, right? Could be, better. Right. Are there any questions, guys, before we get started with this part? Nope, everyone good? All right. Okay, so let's go ahead and try this out. We have here Torch, NumPy, Torch Vision, you're familiar with, Matplotlib, Pandas, NumPy, and the PIL image library. It's loading. Whoops. And grab the next one. Still going. All right, so it finished that. I've got sklearn, same things as before, MLextend for plotting, so it looks nice. And I had run that already. Okay, here we are. Yeah, and like I said, the great thing about this is, it demystifies, you're no longer like, you can see everything, right? The inner workings of all these algorithms and how they're built from scratch. Torch. Guys, any questions over there? All right, so Torch utils, Torch optim, functional. Okay, got that in there. Parameters, same thing as before. Number of epochs is going to be, you can see I have 30 and 27,000, right? But we do have GPUs, so we'll come back. I don't remember how many iterations it took. And this is the simplest approach. I've taken the simplest architecture that I can think of. The batch size is 32. The learning rate here, 0.003. Okay. All right, MNIST, as I said, as promised, same data set as before. MNIST, you guys remember we've been using this. Okay. MNIST test. We've got MNIST train and test. Okay, there we are. And then we're going to convert these to true. Notice we're using the same approach as before. Data's MNIST, train true or false, download true or false, and we use the transform compose to convert this to a tensor already. The images. All right, so we have that already created. So a lot of this is pretty easy to understand. What's going to be hard actually is the training function, right? That's going to have all the new ideas, the fact that we really have three optimizations going on sort of at the same time. I've kept it the simplest that I can do here. Let's look at an image just to remind ourselves. So this should be some image, and we can see that looks like a 5, right? Looks like a 5. All right. Now we can take a look at the tensor just to get a feel for it. It's MNIST, so there's going to be 60,000 images, and remember the images are 28 by 28. Since I'm not using CNNs here, I'm going to spaghettify them. But if you were using CNNs, etc., you might consider, then you can keep them 28 by 28. Okay, so that's done. We can print out the shapes, and actually I already printed that one. So let's do this one. $10,000, 28 by 28. Funny story about this algorithm GAN. So it was invented officially in the paper. The key paper is by Ian Goodfellow. There's this gentleman, Schmushauer, something like that. Anyone, does that name seem familiar? I forget his name, but Schmushauer. He says he invented it in the 90s. So you can always go back to a paper in the 90s that seems like they were doing it. So there's been some debate, but anyways, just the point is that in research, for those of you that will do research or something, this can happen, right? You think you have this great original idea. It's very hard actually to have an original idea. Even something like this by Ian Goodfellow, somebody from the 90s claims that, I think it's Schmidt Huber or something like that, but he's pretty famous because he's claimed that he's invented a lot of things, and he may have. I don't know honestly, but anyway, officially though, this was invented by Ian Goodfellow. All right, so anyway, so test set is 10,000, 28 by 28. All right, so now let's, you guys are familiar with this part. We're creating the data loaders. We've got the train DL and the test DL. Just like before, none of this, as I said, it's almost repetitive, right? So hopefully you're sick of the repetitive, right? But that's the point, that you now know how to create all these algorithms, and you can see that a lot of this is the same. That you can see, I can say now something that I said at the beginning of the semester: use data loaders, because you can use them for everything and they make your life easier. And you've seen we've used them from LLMs to the most simple linear regression, and now GANs and so on. All right, so I have my train DL and my test DL. Okay, batch size for these is 32, I believe, and then shuffle true for the train DL, right? So we want shuffle as we're training. So as I said, the downside of GANs is that they can be difficult to train because there's two models fighting against each other, right? So that's an issue. But it's elegant. And with these ideas, like GANs was great, stable diffusion dominated, but these ideas are circular, right? So you never know. Somebody makes an improvement to GANs, and all of a sudden, GANs take over again because they fix some problem that they had, right? And so you never know. Right now, the dominant is stable diffusion, but I certainly really liked GANs. All right, so now that's kind of a lot of the normal things. Now we start to get into the utility functions that we will be using. So these are just for plotting things. So this function, as you can see, essentially just plots the losses. Now we're going to have multiple losses, as you can see, not just that one that we've always been optimizing. Now we have multiple losses, right? And notice that I'm going to use the words real, fake, and tricked. to kind of represent what I'm doing. So real is the discriminator, detecting real images. Fake is the discriminator detecting fake images. Tricked is when I trick the discriminator with a generated image. You see this other objective, okay? And so, and this will make more sense later, but I'm going to use that terminology. As usual, the code could be more efficient, faster, etc. It is written the way it is to be clearer, hopefully, okay? All right, this function you guys are familiar with for measuring performance in classification tasks. This one is for plotting the losses so that we can compare them. It's really helpful to see where those losses are kind of meeting, right, as we optimize. So we'll take a look at that one. And now we get into the, the beef of the burger, right? So we get into the heart of this, okay? So you're going to need to generate random vectors as input to the generator, the generator network, right? So remember, we're going to have two. So this is an example. So one is to generate just one vector, not a batch of vectors, right? So remember that we usually train in batches. So that means that when we give an input to the generator, right, in batches, we would need to give a batch of inputs, right? But in this example, it's just one, just to illustrate. So random G vector input. So it means this is a random vector that goes into the generator. If you notice, it's nothing more than a torch dot rand of size 100. Does this make sense? Why 100? Because this worked, right? You usually don't want things to be that big, right? We've seen in the embeddings, we go from 128 to 780, 750 or whatever it is, 712. And so here, 100 works just fine. Remember, this is just a random input to the generator. Unlike NIO, we're not optimizing this input or anything like that. We just need to give something to the network to generate. Later on, we're going to tack on to this something like that, but not here, which would be the condition, right? But we don't need that yet. And then I just return this vector. Does this make sense, guys? So just a random vector. Please let me know if you have any questions. Raise your hand or something like that. All right, so the next step is we're going to do the batch representation of that. So this is the batch representation of that. You can see, same idea, a random vector, but now it is batch size by 100. So I think our batch size was 32, so 32 comma 100. And those are going to be the individual inputs for every one of the 32 images in the batch. Okay? So these are kind of utility functions that we're going to be using. Now we get into the networks. So believe, we've made it, right? This is easy. Creating the architecture it's very easy. What's hard here is the loss, right? In a transformer, this is hard, and the loss was super easy, just cross entropy, right? So you can see how it changes. So here, for reference, I added the DLnet to remind you guys. Remember, we take in, X means, X deviations. We can standardize them in here. We have an architecture. This is probably for Iris, starts at 4, and it produces a vector of 3. So you guys are familiar with all these ideas. Okay? Now, here are the architectures that we can use. So I have a generator net, and I have a generator DLnet. But as you might imagine, they're very similar. They're just... So I'm going to add both and then sort of explain them. So that's the generator normal net. Add it in there. And then let's also add the generator DLnet. And we'll skip this discriminator for now so that we can just focus. All right. So, okay, so this is one of the two networks, the hard one, if you will, or the new one, perhaps just not hard, but just new. So let's take a look at what it is. So this is a generator. So that means it takes in random input and produces the output that we want. In this case, a fake image, but a fake image that's convincing, right? A really good, a fake Picasso or a fake Mona Lisa by Da Vinci or something like that. So notice this generator takes in as input 100. Why 100? Because that's the random vector that we're going to be providing to our model to start. Then it goes from 100 to 256, right? And then from 256 to 784. So as you can see, this is what? A multi-layer perceptron. Notice we have a leaky ReLU in there, which is like a ReLU, but I think I told you guys it lets a little bit of the negative through. A layer normalization, because you normalize the layers now, not just the inputs, right? Neural networks respond better to that. But that's it. And then we have, notice here, we have the last function is a sigmoid, okay? Because we are generating, now this is new, right? We are not generating a regression like before where it was just one neuron, or a classification out of 10, which is a class distribution, or even a multi-regression output, which was, let's say, 4 regression values. What are we generating? We are generating an image. Do you guys see that? And that means an image is, for MNIST, is 28 by 28, but we spaghettify them, so it's 784. So that is why this vector here is 784. Do you guys see that? 28 by 28 is 784. So when we want to see the image, we will unspaghettify it from 784 to 28 by 28. Got it? So that's why the sigmoid here, remember, this is the function that mapped from 0 to 1. So we're just going to generate our values in that scale, and then you can do things like change it to 0 to 255 or something like that. So you guys should know that images in every pixel go from 0 to 255 originally, right? And this is not RGB, this is just black and white. Any questions? So this is like one of the most key insights in machine learning, and especially in generative models. That's why I said what you guys are doing in NIO, you can literally generate images. Because if you look, all we're doing here is a normal neural network as you know it before. All you give it as input is random values, a vector of 100, and what it generates, what you expect it to generate, is a vector of 784 with values in it, whatever it is. Like initially it can be just random things, but obviously you're providing feedback so that it starts looking like something that you want. So once we get this 784, that's our finished product. All right, so you can see here then, once we do the forward in the class, we get a random input, goes into the first layer, and then we do everything, and what comes out is the vector of 784. Make sense? So our input is vector of 100, our output is a vector of 784, and that's it. That's our generator, where the input is random. How simple is that? All right, so it seems no questions. So then let's look at this other one. Is just the same thing, just deeper. You can see I'm not using CNNs or anything like that, just very simple neural network. Vector of 100, some leaky ReLUs, normalizations. This has several layers. It goes from 100 to 60 to 120 to 784. Okay? Again, it ends at 784 with a sigmoid function at the end, activation 3. That's it. That's the generator. So we can play with both of these. I think even the simple one works fine. All right, so we added these. Now, the discriminator is even easier because it's just a traditional classifier that we've been using pretty much, during the semester. So you can see that I have one discriminator net, and that's the one that we can use. So it's essentially just a classifier. And a lot of these things, even LLMs, right? LLMs have this thing, have the GPTs, and there's another variant called the BERT. Very similar. BERTs have a variant called the BERT scorer. And essentially what that is you give it some text as input, and all it produces is one number, let's say from 0 to 1, which is a score. And it just depends on how you train it. Okay? So my point is that that model is created to provide feedback. This model is created to provide feedback. We're automating essentially the annotation, right? You know, by creating this other model, and then they're playing a game essentially. Both of these two, you could almost say they're like playing against each other, right? To beat each other, but at the same, while they're trying to beat each other, both of them are actually becoming really good, which is something that might happen, right? Like if a little kid is trying to learn how to play basketball by themselves, they're pretty terrible probably. And then if they get a friend and they're both terrible, but they play against each other, what might happen? They have a set of rules or constraints. What might happen is they get better. You know, one shoots and the other one blocks, and then they have to learn a variant of that, right? And so that's kind of the same thing here. And they're both learning at the same time. So there you are. So we have our discriminator net here. The discriminator net, what's the input to the discriminator net? 784. Why 784? Because it's the image. Do we need to unspaghettify it? No, 784, and it works just fine, right? We need the 28 by 28 because we're human, we're used to seeing things a certain way, but the neural network, can figure it out. Now, if we were using CNNs or something like that, then yeah, we'd have to make some modifications. But anyway, so you can see 784 goes in to 100, 100 to 50, and 50 to 1. Almost like a regression, right? Except that this is going to be, because it's a binary classifier. We don't have 3 classes or 4 classes. This works just as well, right? So we're going to designate here that 0 is false, 1 is true. Do you guys see that? That's it. Yeah, please go ahead. The what? Because yeah, I see what you're saying. Because this is even simpler than that. This is just, I don't accept what you just provided, or I do accept it. So that's how, in hard line, this is. Fake or real. So 0 or 1. There is no in between. Not 20% real and use that feedback. I'm sure that this question you're asking has been addressed somewhere in the literature. You can look it up if that provides, but the original paper worked exactly like this, and you can see this works fine. Yeah, go ahead. Well, remember that this is a classifier, right? So it's like classifying cat and dog. It's either cat or dog. It's not. So we're making the assumption that, imagine we had a probability distribution that is 60-40. So just go with 60, and it's fake. Do you see what I'm saying? But you really don't want, in theory, 80-20 or 95-5. What do you want? 99.99999.00001. What, right? Because then that's like the best performance. You're trying to create the best possible generator. You use the feedback to optimize the weights. Remember, it's all the same, you know, you wanted to predict 1, you predict 0. That's an error, that's a high error, right? So you back propagate that, the weights are changed. When you wanted to predict 1 and it predicts 1, guess what? What's your error? 0. So then your weights are good. Do you see that? Uh, Yeah, no, I get it. I get it. But this is, as I said, the feedback here is like a classifier, right? So the image is, either 0 or 1. And it's because of the way we're coding the loss function. To do what you're doing, you may need to do another loss function. Do you see that? But not the loss function that I'm using. Okay. Guys, any questions over there? All right, so does that make sense? So this is the simplest example. You can try that. It'll be more complex, unfortunately. And the losses here are going to get a little bit, what I said at the beginning. All of this, I think you guys agree, seems pretty easy, right? So far. But the losses get a little bit confusing. Okay? So with your approach, that may or may not be a little bit more complex. Okay? But let's just see how this works. All right, so any other questions about the discriminator? Right? So notice it produces just one neuron. And that neuron should either say 0 or 1. That's it. Okay? All right, and that's like saying true or false, fake or real. All right. So here's the discriminator. Again, takes 784, goes through several layers, ReLUs, etc., and it produces one last output, and this output is sigmoid from 0 to 1. In the training, we only have 0 or 1. We also don't, and that's actually answers your question for this approach. We don't know if it's 0.20 and 0.80 something. All we know it's either 1 or 0. All right, so let's add the discriminator. Added. All right. Now, we're ready for the hard part. So this is the training loop. As usual, and you can see once we get past this training loop, everything is super easy and we're essentially training. So let's take a look. This is a long function, as you can agree. Now, I made it a little bit longer just so that it's easier to read. Okay? But let's copy it, and then we're going to drill down into it. All right. So this is the training function. We've got some list here just to keep track. Remember, there's 3 types of losses that I'm keeping track of. The discriminator has these losses whenever it sees a real image, it should say it's real. Whenever it sees a fake image, it should say it's fake. That's what the discriminator does. So that's what I'm using for losses real, losses fake. But the generator, its weights are supposed to be really good so that it fools the discriminator. It's all about fooling the discriminator. So here, you notice I called it losses tricked, right? And that's essentially when the discriminator says for a fake image that it is a 1, okay? So you tricked it. Whereas the discriminator for a fake image wants to say it is fake, 0. Okay, so I have these losses. Then over here I have the number of epochs. Notice now we're going to have 2 models, right? G model and D model. Discriminator and generator. Playing against each other. Okay, then I'm going to have, notice over here, D loss Fn. So I have a loss function for the discriminator. But I have 2 optimizers. One G-opt and one D-opt. Do you see that? What does D-opt do? It updates the weights of the discriminator network, whereas G-opt optimizes the weights of the generator network. Do you guys see that? But all the comparison is happening in the context of D-loss. Okay? Even the generator stuff is in terms of discriminator because we only care about fooling the discriminator. There's no evaluation directly of the GAN. It's only through what it produced that went ahead and fooled the second model. All right, so here we have our famous 2 for loops that we've been using all semester, per epoch in range and epochs. That's normal. Then from my train DL, it's a data loader. So 4x comma YB. No mystery there, right, guys? So we have that here. We have our images. Now notice here our images in the batch, because this is how we used it when we built the CNN, had a form of batch 1 28 by 28, correct? But we want to spaghettify, right? I don't know what's the official term for spaghettify. So make the vector as a one-dimensional thing. So that's what we're going to do over here. So this is what this is accomplishing. Okay. So this squeeze gets rid of that dimension, the 1. Now, if this was color, obviously we have to handle this in a different way, but I'm keeping it simple. So we squeeze out that dimension, and then we just reshape, right? So when I reshape this tensor XB, it should be 32 comma 784. Do you all see that? Yes. Yeah. All right. So that's my images, correct? These are the real images. Okay, very important. All right, then I have this section here. Notice I highlighted this section here. These comments are not doing anything, although they look like code, but they're just to remind you. At this point, no G training is happening, right? Only discriminator training is happening. Okay, and then once this segment of code is done, we move to the next section where, yes, generator training happens. So let's break this down into the parts. You can see I have like 3 sections. The first section here, this one, notice, generates a fake image. How does it do that? We invoke the function random G batch vector input, right? Random G batch 32 comma 100, right? The input to the generator. And it goes into what? G model. What is G model? The generator network that expects batch comma 784. Or sorry, batch comma 100, right? Guys, everyone with me? The random data. What does it produce? 32 comma 784. These are the images. All right, now we train the discriminator with these 2 sections. One section trains the discriminator to detect real images. So the discriminator does is produce either a 0 or a 1. 0 means fake, 1 means real. Okay. So remember, D model is the discriminator, the classifier, right? So what does this classifier expect? Batch comma 784, correct? The size of the image. Okay. Notice that what goes in here is XB. Do you see that? The images themselves. Okay. The model looks at the images, and what does it say? It predicts a value called D real Y pred. So hopefully for these, it needs to learn. Remember that this discriminator currently in the first iteration has random weights, right? So it's terrible at predicting. But it needs to learn to predict that as a 1. These images from XB are real. Okay? So it's a batch comma 1, but it's 1s. All right, great. Now that value, D real Y pred, goes into D loss FN. And what does D loss FN optimize? It compares the predicted 1 or 0 to torch 1s. What is torch 1s? 32 comma 11111. Do you see that? So this is just, if it was in batch, it would literally just be a constant that is the number 1. Do you guys see that? So constant 1. This is initially, I don't know, 0, 1, whatever it's learning. But as it's learning, as the weights of the discriminator are becoming good, whenever it sees XB, which is real, this is a 1, 1, 1, no error. This is the most important part to understand, right? So if you have a question, ask it right now. Okay? Do you have a question? Yeah, so let me explain it without batches. Without batches, it'll become simpler. Okay? So forget that there's a batch. There's only 1 image. Okay? So here, I did this. I'm not using this yet. But I give it a random vector of 100, and it produces 1 image. That's spaghettified, so it's 784. That's done. Okay. Here, I invoke D model, the discriminator, which takes 1 image that is size 784, and it needs to say if it's real or fake. So it needs to give me either a 0 or a 1. Initially, the discriminator has bad weight, so it's producing a value between 0 and 1, right? But the loss is very fixed. The loss simply says that here I provide the value that I want, 1. And this is the value that it predicts. So I need to minimize that error. Do you see? So when I have updated the weights correctly, it's going to say for real images, guess what? That's a 1. 1, comma, 1 compared to 1, 0 error. Therefore, you did a good job. All right? So that's the objective of this example. Does that make sense, guys? All right, now let's look. So let's finish this part, like the mechanics. That's the idea, right? So we have this loss over here, right? Then we have our familiar 0 grad. So notice we have a d opt, okay? We do our d real loss, this one over here, right? Backward, remember, we calculate the derivatives as we saw last week. And then d opt step. What do we do there? Optimize the weights of the discriminator. So we're doing this, training it what real images look like. Okay? Now let's look at this part over here. The discriminator here, and again, I'll stay with the idea of a batch of just 1, right? So what does it get here? The D model, this D model is the same as this D model, right? So what is the discriminator getting here? The generated image. Is it 784? Yes. It's right? Because that's what the generator produces. A vector of 784, if we unspaghettify it, is 28 by 28. So this is the fake image, unlike this one, which was the real, but everything else is similar. So now, what does it need to learn? Whereas here, it needed to learn that it needed to say that it was a 1. What does it need to say here? 0. It needs to say this is a fake image, therefore, dfake y pred is a 0. Okay? So how do we train it to do that? Well, very simple. In the dlossfn, which is the same as this dlossfn, we give it what it predicted, dfake y pred, but notice that instead of providing torch 1s, we provide torch 0s. You see that? So in terms of a constant here, we're saying this is a 1, the real is 1, learn to predict that this is a 1 because they're real images. Here, this is a fake image, therefore the constant is 0, learn to predict 0. Got it? So the discriminator gets real images and fake images. And when it gets real images, the loss is in terms of compared to 1s. When it's fake images, is compared to 0. And that's it. Now that we do that, we dlossfn, we do the dot backward, calculate the derivatives, dopt dot step, update the weights. So it's learning things that come from the generator are fake, things that come from the real data set are real. All right? So now the thing is, the generator, though, has this other objective, which is to fool the discriminator. So how do we do that? That's the trick, right? So any questions on this part, guys? Any question on? All right. So hopefully that made sense. So now let's move to the magic of the generator. So if you notice over here, notice here we're not going to update the weights of the discriminator. Like the discriminator already had its chance to be trained, right? We already trained the discriminator on real images, fake images. Nice job. Now we go to the generator. That's what we want to train. So how do we do it? Notice here I'm going to use another image over here, generate another image, just to keep it simple. So I have random G batch vector input, right? So what is this? The batch of vectors of size 100, which are the random inputs. Got it? Okay. To keep it simple again, I'm going to switch back to, let's not assume batches and just one item. Keep it simple. So a vector of 100 goes into Gmodel, and Gmodel does what? It generates an image, right? A vector of 784. But now take a look at what happens here. So that image that I just generated from the generator goes into D-model, the discriminator, right? We're trying to fool it. So notice, gen image goes into D-model. D-model produces what? 1 or 0, right? That's all it produces. But I'm calling this variable D-tricked Y-pred. And now it goes to loss fn, right? The same d loss fn that I was using up here. Notice it's the same, d loss fn, right? And that's, what I predicted goes in here. Now the key insight is that this label is now a different label than before, right? When we were training the discriminator, whenever we gave it a fake image, our goal was to train it to predict that it was fake, so 0. But here in this step, guess what? Torch dot ones. Seems crazy, right? But we're trying to say, okay, also, you discriminator become good, but also generator, I want you to become good. What's my objective with you? You need to notice how it works. You give it a random vector to the G model. G model generates an image. That image goes into the D model, and the D model needs to say that this is what? 1. If it says that that fake image is 1, it's saying that that's a real image, which essentially means you've tricked it, which essentially means you've generated an image so good that you fooled a discriminator. So that's why it generates D-tricked, and that is compared to a 1. So it needs to update. Think about it. Initially, this value is very bad, but as you update the weights and improve the weights, it starts to produce 1s, right? So that means that the images you're generating are fooling the discriminator. Remember, we don't really care about the discriminator in this exercise. We're not using the discriminator. We just want a really good generator. All right, so I have my loss, and now comes another part that's a little bit different. Notice that although here I'm only doing d-trick loss dot backward, so because that's really what the loss is, right? The loss is in terms of d loss, and so I calculate the derivatives for that part of the computational graph, and then I update gopt dot step. If you notice over here, I was always updating dopt, right? So what am I updating in dot step? The weights of the discriminator. In this part, I update the weights of the generator. So it's almost like like you get your turn, and then now you get your turn, and now you get your turn. So you can see how it's discriminator, generator, right? They're not in parallel exactly. They're in sequence, but one after the other. That's it. If you understand this concept, you got it. And that's GANs. So that's why I said, it's so elegant. It's not as powerful as other generative image models, but maybe in time, somebody will make an improvement because the idea is great. All right, so that's it. So that's the function. And then this code here is just printing out the losses, which we expect them to, meet somewhere, right? The losses. All right, so that's done. So now let's go ahead and train it, right? So we just have to instantiate a few things. Here we are, and run the model or the training. I'm gonna redo it again on GPU just so it's faster, but we're almost there. So what do? We instantiate G model to be generator net. I already discussed that. We instantiate D model to be discriminator net. I already discussed that. We have a BCE loss, which is a binary cross entropy loss. So it's another type of the idea is still cross entropy without a doubt. This is just binary. If you guys remember, it's more specific. We just have one node, if you remember. So I have D loss Fn, right? You guys see that? D loss Fn. And then here I create two optimizers. every time this semester we've only used, even for the transformer GPT, we only had one, but here we have two, gopt and dopt. Now notice they're both torch.optim.atom, but notice that the parameters are different, right? Gopt is tied to the gmodel.parameters, the weights of gmodel. That's like satisfying, right? It makes sense. And then dopt is tied to the dmodel.parameters. Do you guys see that? And then we just provide the learning rate and so on. And then these parameters are just passed to the training. Any questions? So pretty straightforward. So let me just, at this point, restart the runtime, because it'll be faster if I just use it. Even though I have to rerun all this code. I just don't like using up all that GPU for an hour without actually using it. All right, so yeah, that resets everything. So let's go ahead and give it a try. Okay, so that's good. That one's good. This one's good. The parameters, data. Data sets, the image, shapes, data loaders, printing functions and utilities. Architectures. All right, so we're almost ready. Here we are. So we should start seeing. I'm only doing 30 iterations, I believe. Let's take a look at how long it takes. All right, while it's doing that, we can go back to the Jupyter Notebook. You can see it's just going to print the losses, but now we have 3 losses, right? So, yeah, it's 30 iterations. And then when it makes, this data is hard to read a little bit, so that's why a graph looks better. Okay, like this. So let me see. All right, so it did 1. I just want to see, okay, it's done 2, so it's going to finish within 10 minutes. So that's good. So let's go back here. While it's doing that, we can take a look at this graph, and you can see I'm printing the loss for real, for fake, those are the discriminator losses, and then also for tricked, which is the loss of the generator, correct? So they're blue and orange. You can see blue and orange here. So the discriminator, you also want those losses to be low, right? And they are low, but they're not totally going down because they have to give way to the loss of the generator. So that's why they kind of, if you look at it, they're like meeting like this. The loss of trick, the green one, is the generator loss, and you can see it's going down, and then it sort of stabilizes a little bit. Does this make sense, guys? You can see these are the losses that we have, and then all we're going to do is we're going to generate, use our generator essentially, right? So let's see where we are. So it's at 3, okay? So it's still going. So it's going to take a little bit, but let's grab a little bit of the code and see how far I can get explaining this. We are going to take a 10-minute break shortly, so it should be done when we're back. But let me add this part and explain it. So this part, if you notice, once the generator is trained, what do? We just need to use it, right? That's really all we care about. Now, could there be situations where we need the discriminator for something? Sure. Sure. Right? Let's say that you're in a the forgery detection business, right? And as an art dealer or something like that. Maybe your goal was to train a discriminator for whatever reason. And so that this could be a valid training methodology. But in our example, we're trying to train a generator. Okay? So now that the model is trained, the weights of it are solid G model. We give it still, notice, random G vector. Notice here I'm not using the batch function, but just instead the other function, because I just really want to generate one image. If you gave it the batch one, it would give you a whole bunch of images based on your application. So this is going to be my test, my gen test image 3. And notice, remember, this is going to be a vector of 784. So what do? We unspaghettify it, reshape it to 28 by 28. And then once that's done, we detach it, make it into NumPy, and use pltimshow to look at the images. Okay? So this is essentially what we do. So let me grab a few of these. Let me just have the code ready here so that we can give it enough time to train it. It needs to do 30 iterations, so it's going to do a little bit. Now, they're not as good, remember, because I only gave it 30 iterations in the interest of time. Try more iterations, obviously, improve the architectures. There's a lot of things that you can do. In this case, I'm only doing I really just needed to copy one because I'm giving it random input every time to produce an image that looks like something. Okay. But yeah, so it's still training. It's at 9 out of 30 right now. So let's, once it gets to 29, we will print the losses. Oh, I forgot to add this part. So we need to print the losses. All right. And hopefully it'll start to generate images. You can agree, all of you, that this is not noise, right? This is an actual image that was generated. The only problem, this is what? What number is this, would you say? A 5, right? What about this one? A 4? Okay, good. What about that one? A 5, yeah. And so you can see, you can make out more iterations better. Also, this coloring that I'm using is not really that it's generating in color. It's just like a little filter type of thing that I'm using to make it look nicer. It's still grayscale. All right, so it is 6:20. All right, it is training. Oops, let's look over here. So it's at 11. So let's take a 10-minute break, all right, from 6:20 to 6:30. And then when we come back, I'll start with this, just show you the results. We'll finish it up, and then we will move to conditional GANs, which, as you might imagine, very similar, but with a little tweak. All right, so this concludes sort of the GAN algorithm, and then I'll just show you the results when we come back in 10 minutes. So I need to stop sharing, and I'll end this video here.